So welcome back to the video on types of nuclear reaction, this card sorting. Now what we're going to do is we're going to talk about radioactive decay. So let's go back to our first slide. Spontaneous fusion reactions also fall under the category of radioactive decay. Radioactive decay is the spontaneous breakdown of an unstable nucleus known as a parent isotope into a more stable nucleus, the daughter isotope, by release of energy and radioactive particles, i.e. radiation. So during a radioactive decay, you have something that's unstable, and things tend towards stability. Just like this is the reason why if you put a ball on top of a hill, the ball starts to roll down the hill on its own. Everyone always says gravity, which there is a force that's pulling it down. But what it's really trying to do is trying to get to a lower energy state. It's losing that potential energy and converting it into kinetic energy to get into a lower energy state there. And that's what happens in the world. Things tend towards a lower energy state. And if you take a look at your bedroom and it's not looking very neat right now, well, you can say it's the law of physics. So with that being said, same things happen during radioactive decay. You have something that's unstable and it's going to break down spontaneously, that means on its own, into something more stable. Now, if the daughter isotope, so what you make, is smaller, is a smaller nucleus than the parent isotope, then that radioactive decay will also fall under the category of fission. So some types of radioactive decay will fall under the category of fission. Now, since radioactive decay is spontaneous, means it happens on its own. And by the way, spontaneous doesn't mean it's fast or it happens like that instantaneously. It may take a long time to happen. It just means it happens on its own. You don't need to do anything for it to happen. Since it's spontaneous, no neutrons are needed to initiate the reaction. So remember, we said for fission, sometimes you need to initiate the reaction by flinging a high energy neutron into it. With radioactive decay, you don't need that neutron. And so therefore, all radioactive decay reactions will have only one reactant, i.e. the parent isotope. So you should only see one thing on the reactant side if it's a radioactive decay. If you see a neutron on the reactant side, you know it's not radioactive decay because that means that reaction was not spontaneous. Now, there are different types of radioactive decay, which are classified by the type of radiation that's emitted from the reaction. And you need to know 3 of them. There's more than 3, but these are the 3 you need to know. And that's because these are the 3 that people are engaged with the most. Alpha decay, beta decay, and gamma decay. And in fact, because you have carbon-14 in your body right now, you have radioactive particles that undergo beta decay. So you're radioactive. All right, so let's talk about alpha decay. Alpha decay involves release of alpha particles, which are high-energy helium nuclei. So then they can have this symbol here, helium, or the alpha symbol. And it's helium-4, so you have the mass number 4 and then the nuclear charge number, or you can also think of it as the atomic number if it's an element of 2. Beta decay releases a high-energy electron called a beta particle, and so it has a mass number of 1 and then a negative 1 for the nuclear charge because electrons have a -1 charge. And finally, gamma decay. Gamma decay is a high-energy photon, so a high-energy photon of light, a packet of light energy. It has no mass and it has no charge, so the only thing that changes there is just it releases that energy, but the mass and the charge numbers stay the same. So let's get back to our card sorting, because now what we're going to do is we are going to look at what we have in the fission, the transmutation boxes, and also what we have here that didn't fit in any category, and see if they fit under radioactive decay. Alpha, beta, and gamma. Now, fusion we don't need to worry about because fusion you're bringing 2 or more things together to form a larger nucleus, and that's opposite of decay where you're breaking something down. Let's begin by the ones that are uncategorized. So take a look at these, C and K. So we have, for example, barium-137 to form barium-137 and this particle here. What type of particle is that? Well, if you said gamma, you are correct. And so therefore, this one's going to go under gamma decay. So we're going to move C here. And that star, by the way, just means that you have an excited nucleus. It has a lot of energy. All right, what about radon? 222. Yep, so K will also go under gamma decay. Once again, you can tell because it has a gamma. So on the product side. So if you look at these reactions, you notice have the same sort of pattern here. One reactant or parent isotope, and two products or daughter, one of which is a daughter isotope, a stable barium, and then a gamma particle. So you know it's gamma because one of the products is gamma particle. Okay, now let's take a look at what we have in the fission category and see which ones of these can fit under alpha, beta, or gamma, if any of them can. Let's take a look at G since that one's sticking out first. So we have polonium-218 forming lead-214 and an alpha particle. So what do you think that fits under? Absolutely, that is alpha decay. Once again, you start with one thing, your parent isotope, and you form two things, one of which is your daughter isotope and the particle for which that type of decay is named, an alpha particle. Okay, next one I see here is L, so let's take a look at that. Oops, the other thing I forgot to do is because this fits under fission and alpha decay, I'm going to make a copy of that. I'll make a copy of that box there. I don't know where it went, but hopefully, did I make a copy? Yeah, I did. And I'll make sure that we have one to put under fission and alpha, just so we can see that sometimes things fall under multiple categories. Okay, cool. So looking at L here, which is our next one, which one do you think this falls under? Take a look at that. Is it just fission or is it one of these types of decay? And if so, which one? Now, if you look at this and you say, oh, helium-4 is an alpha particle, so that goes under alpha decay, you wouldn't be quite right, because if you take a look at it, notice that with alpha decay, you only have one reactant. Here you have two things. You have your reactant, lithium-6, and then you have this neutron. Remember, the neutron tells you you need a little help to get this reaction started. So that makes this reaction non-spontaneous, and all radioactive decay are spontaneous, so they'll never have a neutron there. They don't need anything to get the party started. They got enough energy to do that on their own. So that one's just going to go into fission. How about A, though? What would you put that under? One reactant, two products, one of which is a helium-4 nucleus, also known as an alpha particle. You got it. That goes under alpha decay. And once again, I'm going to make a copy of that because that can fit under fission as well. And then what about the last one here? We have a neutron, uranium-235, forming these different types of nuclei, barium-141, krypton-92, and then also 3 neutrons. You got it. That stays under fission because we have we have the neutron, so that tells us this is not non-spontaneous. Also, none of the things that we formed here would fit under the category of alpha, beta, or gamma particles. You always want to look for one of those particles on the product side to see if it's that type of decay. All right, so we can go ahead and put these back. And they kind of get an overlap there, but that's fine. These are all fission. So your fission reactions would be A, G, L, and E. Now let's take a look at the transmutation. So let's start with the top one I see here, I. We have potassium-42 forming calcium-42. And do you know what this particle is? That's a beta particle, right? So what do you think that goes under? You're absolutely right. It goes under both transmutation and we're going to put it under beta. So I made a copy to keep under transmutation. And then let's take a look at H. Do you see, well, we have 2 reactants, so automatically I know this is not a decay, so I can just leave it. But you can also check on the product side and see if you see any alpha, beta, or gamma particles, and you don't, so we can just leave that. How about F? Well, if you look on the product side, you will see, oh, there's an alpha particle here, a helium-4 nucleus. But once again, we have 2 reactants, and for radioactive decay, notice they all start with just one thing. And our last one here. Carbon-14 to form nitrogen-14, and this, what's this particle called? It's a beta particle. So if you see a beta particle on the right-hand side, it's a big clue that it's radioactive decay, beta decay, but you also want to make sure you just have one reactant, which we do, one parent isotope. And we're going to pop that over here in beta. And we also need one for transmutation, so I made a copy. All right, so now we have our transmutation one sorted as well. Nice, nice. So for under transmutation, we would have B, I, H, and F. Under fusion, D and J. Under fission, A, G, L, E. For alpha decay, we have G and A. For beta decay, we have I and B. For gamma, we have C and K. So I hope that helped. I want you to take a look and see how some of the things do overlap. Like for fission, alpha decay also falls under the category of fission. And beta decay falls under the category of transmutation. Whereas gamma is just under its own thing. It's just gamma decay. All right, hope this was helpful. There are some discussion questions you might want to think about to help solidify your understanding. All right, folks, have a quality day.